Welcome back to part 2 of our general equilibrium notes for AP Chemistry. We left off last time doing a calculation for equilibrium constant, that is capital K. We looked at how you can reverse the direction of the reaction, and what that does is inverts the K, and you get your new K. We looked last time at how you can add up several reactions, and when you add up the reactions, the K's multiply together to get your overall equilibrium constant value. It's a great place to continue in our notes here, as I want to do some review of equilibrium. When we're asked to write the equilibrium constant expression, it is this that you're being asked to write. That K equals, and then you put your, check it out, it's always going to be products over reactants. Always, guaranteed. Always products over reactants. Whatever way that the equation is written, the products go on the top, the reactants go on bottom. Now, how would this change if the number of products or reactants was different? Now, I need to point this out because otherwise students, for some reason, infer something that is not there. This is a very pretty looking form of the equilibrium constant expression where we had two reactants and two products. It is not at all a thing that you have to have two of each. You can have, of course, any number of products and reactants, a number greater than 1 or greater. So if I only had one product, I'd have only one thing on the top. If I had only one reactant, I'd have only one thing on top. If I had 5 products, I'd have 5 things on top. If I had 5 reactants, I'd have 5 things on bottom. So just because in general it looks pretty to do A and B and C and D so things line up and have some sort of symmetry going on, it certainly does not have to be those numbers. Don't get caught on, oh, it has to have so many values. It must be the products raised to their coefficients divided by the reactants raised to their coefficients. Okay. Now to do this, as I just mentioned, the coefficients, see how the coefficients are the exponent? That indicates to us that we are assuming the mechanism is one step or that the equation we're working with is the slow step. That is an assumption we have to make in order for this to work. And that is an assumption we will make in order for this to work. That is an assumption there. Also, we assume we do not include pure solids and pure liquids. Now let's discuss why. Why would we not include pure solids or pure liquids? Well, square brackets mean concentration of. So say I have a beaker and I fill it with water. What is the concentration of that water? I know, it makes your head hurt, doesn't it? Because we don't do that. It's a pure substance. There's nothing dissolved in it. You can't have a concentration, that is, you can't have a solution if there's nothing dissolved in something else. So whichever way you look for it, either nothing's dissolved in the water or the water's not dissolved in something else, it's meaningless to say that we would have a concentration for it. So pure liquids, like water, are not ever included in our equilibrium constant expressions. Also solids. So that represents a pile of salt on the bottom. Okay, so I have sodium chloride solid. And it's just sitting there at the bottom of my beaker. I would not include that in my equilibrium constant expression. So the question is, why would I not include that? And again, concentration, which we will measure in molarity, just to review, is how much dissolves. This solid that's sitting at the bottom is not dissolved. Since solids aren't dissolved, we would not measure a concentration. So we're not going to include those as well. Furthermore, the amount of change we will get in a chemical reaction, if I have 250 milliliters of water, the amount of change to that amount of water is going to be very minimal. So it's not really worth keeping track of. And the amount of change to a whole large pile of salt down here at the bottom of the beaker is not going to change much whether or not I'm at equilibrium. So again, it's also not worth looking at. So we do not ever include pure solids and pure liquids. How would you know if you have solids and liquids? They would tell you. We could say solids with a little label S and liquids with a little label L. They could say solid sodium nitrate is dissolved into, okay, and then when they say solid sodium nitrate, you know, oh, that's a solid. We're going to start with the solid, not going to include that. Anything dissolving in water, they might even include, as you'll see later on, water in the reaction, and we're not going to include that. So have I said this enough times in enough ways that you should never include a pure solid and a pure liquid in this equilibrium constant expression. Okay. Now Kc can also give us an indication of how much a reaction has occurred, or the activity of the reaction, to put it in other words. In other words, the bigger the Kc, the more products and less reactants. Well, let's go back and explain that. I say go back. There we go. So, what do we know about the size of Kc and how much the reaction has occurred? Well, check it out. Kc is always products over reactants. If the reaction has occurred a lot, I should have a large amount of products. And if it's occurred a lot, I should have a very small amount of reactants left. A number that is, large divided by small, that's going to be a number that is much greater, probably much, much greater than 1. Now, what if it's the other way around? What would it be then for, well, that didn't work. Let's try that again. What would it be for a reaction that doesn't occur much? Okay, well, again, products over reactants tells us we're going to have a small number on top and a big number on bottom. Lots of reactants left over, small amount of products made. Okay, that should be a case that is less than 1. All right. Is it possible for a K to go negative? No, a negative K is meaningless. Now be careful. By a negative K, I mean I would not be able to write Kc equals negative 0.05 whatever. Okay. That's the negative I'm talking about. Kc can certainly be having a negative exponent. That is a possibility. That's fine. What it cannot have is a negative in front. There is no way in this equation to get a negative to work out. So if you have a negative Kc, you did something wrong. Go fix it. Okay. So what would be the Kc for no reaction? So I start out with my products. Wow, I killed that. Reactants. And I get my products, and we do products over reactants. Well, if there's no reaction, then there's 0 products. And so my Kc would be 0. What would it be for a strong acid, strong base? Now, by definition, we're going to say strong acids and strong bases ionize completely, meaning we have 0 reactants left and all products left. Okay. Now, this is going to be difficult to calculate because when we do concentration of products divided by concentration of reactants, we're going to get a huge number on top divided by 0. Okay. And you're like, oh, you can't divide by 0. Okay. So, if we can't divide by 0, what do? Well, we assume that you'll have a tiny itty-bitty amount of that left. So let's maybe just throw in a lot of zeros and a 1. I have that much reactants left. Then I'm not dividing by 0. I'm dividing by a very, 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 very small number. And you can imagine that's going to make Kc enormously big. Maybe I'm just randomly throwing in a number. But I do, come on, I do want you to see how this would look. Check that out. Check out the size of that exponent. Positive 34, meaning there are, 33 zeros after that 0. That's a huge number. It is absolutely, totally, completely possible to have a Kc value in the millions, billions, trillions, even beyond. That would tell us lots and lots and lots and lots and lots and lots and lots of products and very little reactants are left over. It is also possible to have it be the other way around, with a negative 34. And that would tell us, now notice where I put the negative, that would tell us lots and 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 lots of reactants are still around, and just a tiny bit of products have been made. What can Kc not be? Kc cannot be a negative number. I'm not saying exponent, I'm saying number. The whole number cannot be negative. It must be positive. The bigger positive it is, the more the reaction goes towards completion. And honestly, for a strong acid or strong base, we honestly typically don't list a number. We don't even bother trying to calculate it. But if we did, and you looked up the number, then you would see it'd be probably a very large positive exponent because we expect lots of products, extremely little reactants. If it's a weak acid or base, especially if it's a super weak acid or base, okay, then we would possibly get a negative there. Again, that tells us a little bit of products were made, and most of it is still there as reactants. And we can get all this math I've been discussing with you, we get just right here from this formula. So be able to memorize so that you can write this formula. Be sure that you write it the first time you start any calculation, and you mathematically use what it's telling you. If you're like, oh, well, it went very far, so we have huge here, we have little here, then you can mathematically get the answer without even actually doing anything on the calculator. You can know if it's going to be enormously big, enormously small, or what the relative amount should be. Okay, let's do an actual example finally. So, now with numbers, and it is good to know it without numbers so that you're ready for the multiple choice portion of the test, but with numbers, let's practice. Notice I have a rice table. Notice that they've only filled in numbers for the equilibrium, but you know what, that's fine. That's all we really need to write an equilibrium constant expression and calculate Kc. So always, 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 always write your equilibrium constant expression. Kc equals product is NH3 raised to the power of 2. Reactant is N2 raised to the power of 1, and H2 raised to the power of 3. Could be a point just for writing that, so get that super easy point. Okay, you want that super easy point. It's great to do. Gets you started, show your work anyway, so you're going to write that anyway. Now we plug in our equilibrium values. At equilibrium, our ammonia is 0.565 moles. Okay, oh, check this out though. This is moles in a 5-liter vessel. So that's moles per 5 liters. And that's going to be squared. And my N2 is 3.01 moles, also in 5 liters. And my H2 is going to be 2.10 moles, also in 5 liters. And that's going to be cubed. Okay, so if it looks funny to put fractions into your equilibrium constant expression, then do the work up here. Be like divided by 5 liters equals this divided by 5 liters equals, and this divided by 5 liters equals. Okay. Yes, you can put moles into a rice table. If you put moles into a rice table to calculate Kc, you must have it in concentration, and that's molarity. So whichever way you look at that, be sure that you take care of it either here in the table or here in the math. All right, so let's do some calculator time. Yay, calculator time, or something like that, right? Proves you know how to use a calculator and you know some basic math, not that you know anything about chemistry, which is why they really are shying away from you doing actual calculator math on the test. What would you be expected to do on the test? You'd be expected to do mental math. And so you would be expected to somehow do this sort of thing in your head. So they would give you numbers easy enough to do in your head. You'd be expected to simplify. I'll show you as the chapters move on some little simplification tricks we have that work really well, things like that. Okay, so anyway, pull out your calculator, give this a try. Maybe pause if you need, and let's see if you get the answer that I get so that you know you've got what's going on. Okay. If you've not had enough time to calculate it, pause it now. And since I have 3 sig digs given to me, I'm going to round to 3 significant digits, so 0.286. And our label on equilibrium constant is unitless because we make it work out that way with the way that we handle fugacity and equilibrium numbers. So it's going to be weird at first to see a number so often unitless, but that's the way it's going to be. Okay, so there's my equilibrium constant expression with solving for k. That's my equilibrium constant value. So equilibrium constant expression, equilibrium constant value, or the value of my equilibrium constant. Easy enough math, really, once you plug it in. Okay. So let's try a harder example. Now, what's harder about this? Well, they didn't give us the numbers to plug in first, so we need to find the numbers to plug in, which is why we love rice tables. I mean, if you build a rice table correctly, you get all sorts of information. And there are many times where on the test, in a large calculation type question, there's points for correctly setting up a rice table. Yes, you get those points if you do the same math some other way, but really I don't know why you'd want to function without a rice table. Let's check out what we've got going on here. We've got our reaction, and it does seem to be balanced. You might just double check it real fast. They do also say things like the balanced chemical equation for the reaction below is, and they'll tell you then that it's balanced. But if they don't tell you that, take the 10 seconds it takes to double check. Be like, oh yeah, 4 N's, 2 O's, 2 O's. We have initial amount, so you can see I have nothing but reactants, no products. And now I have an equilibrium amount. So what must the change have been to go from 10 to 2.20? And I like writing it this way. Okay, 10 minus 2.20 tell me 7.8. But here's what's happening. I like putting the minus sign there to let me know I am losing. I am losing 7.080 moles. If I don't put a minus sign there, you might be tempted to add. And that's why I like showing the minus sign there. Because on the other side, if I lose reactants, if I use them up, I should be gaining them on the product side. 2 to 2 ratio. So this is still plus 7.8 moles. Okay, notice how the ratios are the same in the coefficients. So I can add this up. And now I have a 2 to 1 ratio. So I need half of that, which if I do the mental math correctly, and you could grab a calculator, okay, we've got 0.390 moles of that. And so I can add it here to 0.390 moles. Now, this is all done in a 2-liter vessel, so why not divide at this moment by 2 liters? So I have 1.10 molarity left over of the N2O, that's the dinitrogen monoxide. I have 3.90 molarity of the nitrogen gas made. And I'm going to have, so we're going to divide that, 1.95 molarity. Yes, that seems good. 1.595 molarity of the oxygen gas made. And now I'm ready to find my Kc. And again, I'm going to get that point. If it ends up being a point, it is well worth the time to write this correctly and get the point. So concentration of nitrogen squared, that's my first product. Concentration of oxygen, no exponent because it's a 1, divided by concentration of dinitrogen monoxide squared. Now I substitute in my numbers. my equilibrium number in molarity, that's what those square brackets mean, molarity, you must be filling them in with molarities. I have 3.90 molarity of N2, and that's still going to be squared. Don't forget, that's one of the most common mistakes. Students forget the square. They forget to carry it over, so don't forget that. 1.95 molarity of oxygen divided by 1.10 molarity squared there. The labels will end up canceling, and so all I have left to do is put this through the calculator, and again, yay, it's calculator time. Okay, so we're going to do 3.9 squared times 1.95 and divide that by 1.1 squared. If you want time to put it into your calculator, then pause here. And I get 24.5. Okay, no label, not molarity, nothing else, no label. My equilibrium constant is 24.5. What's that tell me? That tells me I certainly have more products than reactants. That tells me that this reaction went pretty well. But that makes sense considering I went from 10 to 2, and so I definitely used up a lot of reactants and I gained a lot of products. Okay. So the actual size of this number does not tell you a whole lot unless you have some very large exponents, so either positive or negative. But we do expect k values to be, somewhere, any number. It can be any number that is not a negative. So don't be thinking, oh, k must be positive and greater than 1, or k must be positive and less than 1. It's got to simply be positive. Okay, so that's how we would do that. Now I want to mention that we've been doing Kc, that is equilibrium constant with concentration, so we can just as easily do it with pressures. And so we get what we call a Kp expression. And notice how it is extremely similar to Kc. One big, super big, super big, don't ever forget this is important, difference. Okay, when we deal with pressures instead of concentration, now please understand, you can measure gases in concentration. That is a possibility. But we can also measure gases in pressure. If we use pressure, we do not ever, never, with P's for pressure, partial pressure, would we use square brackets. Because you'd be saying concentration of the pressure of, and that's stupidness. Okay, so don't do that. Yeah, I probably invented a word there. Don't do that. If it's a Kc, use square brackets for concentration. If it's a Kp, use regular parentheses or no parentheses at all because it's pressures. Why call it Kp? Well, you've probably guessed by now that P stands for pressure, to remind us to put in pressures and not square brackets. Okay. Notice the form is the same, products over reactants. That will never change. Every equilibrium expression is the same. We just, a difference between a Kc and a Kp and a Ksp and a K, etc., they're just special Ks. That's all. The format is always the same for all of them. Okay. What would the units be? Well, isn't that kind of a trick question? Shouldn't all Ks be unitless? Nod your head yes. All K should be unitless. There is no label on this K, which is very different than lowercase k, the rate constant, which always had a label that they always would ask you for. They're always wanting to know the label on on rate constant. They will honestly never ask you for the label on equilibrium constant, because that could be seen as a trick question, and they would not do that to you. Still, with Kp, we're not going to include solids and pure liquids. And the reason is this. What's the pressure that 100 milliliters of water exerts? Yeah, it's not a gas. It doesn't exert pressure. What about a solid? I have 52 grams of salt. How much pressure is that? Exactly. It's a meaningless question. There is no pressure for solids and pure liquids, so we still are not going to include them. We will never include pure solids and pure liquids. Lots of good reasons not to. We will not. Do not. In fact, in getting the point for writing the formula, that's one of those things they're checking for is, do you know to skip the pure liquids and pure solids? So please, 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 please be careful about that and don't accidentally include them. What if you have Kc and you want Kp, or you have Kp and you want Kc? Well, we have a way to convert from one to the other, and isn't this a lovely looking formula? You have a pressure, equilibrium constant with pressure, and equilibrium constant with concentration. We have R, the ideal gas law constant, and we have T, temperature in Kelvin, and we have delta N, the exponent is the change in moles of gas. Okay, let's say, I'm going to give you a tale of two reactions. Let's say I start with 1 mole of a gas here, and I'm adding it 1 mole of a gas there, and I make 3 moles of a gas there. And I know that because the stoichiometry is 1 to 1 to 3. The coefficients are 1 to 1 to 3. That's going from 2 to 3. Now we go backwards, products minus reactants, so 3 minus 2, that would be a change of 1. What if I started with 3 moles of gas there, because I had a coefficient of 3, and I end up with 1 gas there and another of a different gas there? Well, that's a change of 2 minus 3. That's a change of negative 1. And we would, yes, we would put a negative 1 exponent in there in that situation. So it's by delta N, it's the change in the total number of moles from reactants to product side, but go products minus reactants. By the way, changes have always been products minus reactants. Change in temperature with MCAT is temperature final minus temperature initial, or temperature products minus temperature reactants. So it's always final minus initial, products minus reactants. It's no different. Nothing new. Please don't get it wrong. And it is a total. Get a total on the reactant side, get a total for gas. Now what if it said solid or liquid? Ignore it. Just total the gas amounts, the coefficients on the product side, total the coefficients on the reactant side, subtract products minus reactants, that's your delta N. Interesting thing happens. And since this equation is not on the formula sheet, at least not yet, we keep telling them we'd really like that on there, but it's not on there. What does that mean? That means you're very unlikely to be asked to calculate this, except for they might be clever and ask this question and expect you to know. When would your Kc equal your Kp? When would those numbers be exactly identical to each other? So math-wise, let me do some erasing so we can focus. Okay, math-wise, how can I get this to equal that? Well, notice if those two are equal, this portion has to be gone from my equation. How do I get any number that is being raised to an exponent that, couldn't change to become 1 if my exponent is 0? Now, what's that mean? 0 gas involved? No. That means the change in the moles of gas is 0. Maybe I start with 5 moles and I end with 5 moles. Or I start with, well, I did that backwards. End with 5 moles, start with 5 moles. Or I end with 2 moles and I started with 2 moles. If the coefficients are the same for the gases on both sides, when I subtract, it's 0. And in that particular very curious, very important case, your Kp and your Kc are exactly equal. I point that out because that could allow us to bridge. They could start asking, part A could be about Kc, and part B could also be about Kc. And then they could suddenly ask you if, the change in moles, and they probably won't say that. Here's the balanced chemical equation. You notice the change in moles is 0. Then they could ask you what's Kp. And now they could, D and E and F could be about pressures. They could ask you, Pivnert questions after that or something like that. It's a great way to convert between Kp and Kc and do a connection in chemistry. They love to ask connection questions. So again, Kp and Kc are equal if the change in the moles of the reactants and products, change in moles of gases of the reactants and products is 0. The rest of it, when it's not 0, in class, look up that formula. But on the test, since it's not on your formula chart, very unlikely they would ask you to calculate. Okay, I want to stop there and just do some practice with KPs and KCs and writing them and calculating them, and it's good stuff, and I don't want to add in reaction quotients yet. So we're going to stop there, and good luck on your practice. This is easy. Equilibrium is easy. The good news is equilibrium is a lot of AP chemistry. The catch to it is figuring out where the information they give you goes into all the equations. The equation part is easy. It's doing the detective work to be like, okay, they only gave me this. How do I turn that into something I can put in the equation? And the only thing that makes you good at that is practice, practice, practice. So let's do some practice, practice, practice. Good luck.